All right, so we have spent significant time finding the derivative of a function using one of those two limit statements. So once again, derivative is the slope of the tangent line to a curve at a given point. It is the instantaneous rate of change. It is the slope of a single point on a curve. So we've been working through using those two limits, either as h approaches 0 or as x approaches a. The idea is that this is slope because we're taking 2 points that are getting infinitely close together. And that's the distance between, or that's taking 2 points and we're pushing them really, really close together. Maybe we've noticed that we have the same kind of trends showing up over time. And so rather than using that limit repeatedly every single step of the way, we can look for some patterns and simplify some things. So we're going to look at a variety of different derivative rules for polynomials and exponential functions. And this will shorten the time that we use. Rather than having to go through the limits every single time, we've got rules we can follow. If you're taking Physics C, you've seen some of these rules already. We're going to start off with the derivative of a constant function, just some value. Now we can think that that's a horizontal line, a constant function like y equals 6. Well, the derivative for some constant value, I'm going to set it up looking at our limit. So that's as h approaches 0 of f of x plus h minus f of x all over h. If we plug in our function, f of x plus h is c. F of x is c. Well, evaluating that, it's going to be the limit as h approaches 0 of 0 over h, which is 0. So what we find is that the derivative, and I'm going to use this d dx notation, so it is the derivative of some function, in this case it's going to be our constant. This is saying the derivative of this function with respect to x is always 0. Anytime we have the derivative of a constant, it's always 0. That's a horizontal line, and the slope of a horizontal line is always 0. Never have to apply that limit rule for that again. Next, we're going to have what we call the power rule. So this applies for any time that we have some variable base raised to a positive integer exponent. Something like x squared, x cubed, x to the 6th. What we had done before was we multiplied that out, or we looked to factor things. Now I'm going to take this for some general n exponent. Rather than going through the limit every single time, let's see what happens. So we've already stated that as x approaches a, we've got x to the n, subtract a to the n, all over x minus a. That was like if we had x cubed minus a cubed. We factored that. If we had x squared minus a squared, we factored that. If we had x to the 17 minus a to the 17, you really didn't want to factor it, but you factored it. Well, for some general n, as x approaches a, we're always going to have that x minus a factor, but then we're going to have x to the n minus 1 plus x to the n minus 2 times a plus x to the n minus 3 times a squared plus all the way down to a to the n minus 1 all over x minus a. That was our factoring pattern. You've seen it where x squared minus a squared is x minus a, x plus a, x cubed minus a cubed is x minus a, x squared plus ax plus a squared. We've seen it just like that. Ooh, there's that common factor. So as we apply now, that's going to give us our limit as x approaches a of x to the n minus 1 plus x to the n minus 2 times a plus x to the n, that's the 2, x to the n minus 3 times a squared plus all the way down to a to the n minus 1. If everything becomes an a, it's a to the n minus 1 plus a to the n minus 2 times a is a to the n minus 1. N minus 1 plus a to the n minus 1 plus plus a to the n minus 1. there are n many of those. And we can see that, whereas we had x squared minus a squared, there were 2 terms. X cubed minus a cubed, we get 1, 2, 3 terms. Collecting those, there's n many a to the n minus 1. Ooh, so if f of x is x to the n, we're going to have f prime of x is always going to be n, the exponent, multiplied by x to the n minus 1. We subtract 1 from the exponent. Isn't that convenient? So let's take some examples. What that means here now, x to the 6th, well, that's n. So applying this rule, f prime of x is going to be n times x to the n minus 1. So if f of x is x to the 6th, that's going to give us f prime of x is going to be multiplied by the exponent 6 times x to the 6 minus 1 is 5. Ooh. 6x to the 5th. The exponent multiplies in front, and we subtract 1 from the exponent. That's it every single time. Just changing my notation a little bit, if y equals x to 1,000, y prime means the same thing. Take the derivative of that function. There's our exponent. So we're going to multiply by the exponent, be 1,000, x, subtract 1 to the 999. I don't need to multiply and factor and work through the limit anymore. Changing notation, if I've got y, I am differentiating with respect to t. So the rate of change of y with respect to t, the rate of change, apply my limit rule. I see my exponent. So we have 4t subtract 1, 3. That's convenient. The derivative with respect to r of r cubed, 3r squared. Wow, that is nice. So we never have to apply that limit when we've got a positive integer exponent. Not so bad. Ooh, what about other power functions? Well, we could rewrite this. So the derivative with respect to x of x to the negative 1. Before, we did the limit as x approaches, I'm going to use a of 1 over x, subtract 1 over a, all over x minus a. We got a common denominator. That's limit as x approaches a. That would be a subtract x over xa over x minus a, which is the limit as x approaches a of negative x minus a over xa over x minus a. That cancels. And we've got the limit x approaches a of negative 1 over xa, giving us f prime of x is equal to negative 1 over x squared, which is the same thing as negative x to the negative 2. Look at how that happens. Can we apply that power rule? Yes, we can. So that would give us multiply by the exponent, negative 1, subtract 1 from the exponent. Negative 1 subtract 1 is negative 2. So the power rule applies for negative exponents. Let's check about rational exponents. Well, the square root of x, this would be the derivative with respect to x of x to the 1/2. What we had seen before, limit as x approaches a, b, square root of x subtract square root of a over x minus a. We knew that we're going to multiply by the conjugate. Giving us limit x approaches a, that would be x subtract a over x subtract a, square root of x plus square root of a. Ooh, giving us 1 over 2 root a. And so f prime is 1 over 2 square root of a. As a rational exponent, that is 1/2 a to the negative 1/2. Oh, well, if we apply that rule, multiply by the exponent, we have 1/2 x, 1/2 subtract 1 is negative 1/2. There's our derivative. The power rule applies. So we have this general power rule. If n is any real number, so that is a positive, negative, integer, any fraction, any decimal, pi, if you will, then we've got a rule that d dx of x to any value n is always going to be n times x to the n minus 1. That's a rule. Remember that. So now we can apply, rather than take the limit, this is going to give us f of x, x to the negative 2. So f prime of x is going to be negative 2, x to the negative 3. Done. That's it. Happy days. Let's try another. Oh boy. This is x to the 2/3. So f prime of x, applying the power rule, multiply by the exponent, 2/3 x, subtract 1, 2/3 minus 1 is negative 1/3. That sure is convenient. Let's take a look at some other changes. Or let's actually find another equation. Find the equation of the tangent line and normal line to the curve. Now, a normal line is the curve through the point that's perpendicular to the tangent line. We're looking at y equals x root x, or we've got y equals it's x times x to the 1/2, which is x to the 3/2. I want to find the equation of the tangent line. And I remember tangent line is y minus f of a equals f prime of a, x minus 1. So y prime, the derivative of y is going to be 3 over 2 x to the 1/2. At the point 1, so y prime of 1 is going to be 3/2 times 1 to the 1/2. Okay, our slope at that indicated point is 3/2. So our tangent line, y minus 1 equals 3 over 2 x minus 1. Our normal line, and you may have seen this in physics, the normal force perpendicular to a vector, usually that car on the hill problem. Normal is perpendicular. Slopes, opposite reciprocal. So if we have a slope of 3 over 2, the perpendicular slope is going to be negative 2/3. Our normal line, y equal, nope, take that back, y subtract 1 equals negative 2/3 x minus 1. A few more rules. Constant multiple rule. If we're taking some function and multiplying by a constant, like 3x squared, if we have some differentiable function, then that constant multiple is the constant multiple of the derivative. In a way, we can factor it out or just multiply it. The reason for that, if we follow along, we've got some function cf of x. Well, I can factor that. It's going to be the limit as h approaches 0 of c multiplied by f of x plus h minus f of x all over h. This is the derivative of f of x, and so we have c f prime of x. We can do the same thing with a sum or difference of two differentiable functions. The derivative of a sum or difference is the sum or difference of the individual derivatives. So that enables us to do things like polynomials. So let's take the derivative here, applying our rules. X to the 8th is going to get us 8x to the 7. 12x to the 5th, I'm going to get 60. That's 12 times 5. X to the 4th, subtract. 4 times 4 is 16. X cubed. This is using the constant multiple as well as the sum and difference. 10 times 3 is 30x squared minus 6. And now last one, plus 5, that's a constant, so that's 0. There is our derivative. Wow, this goes a lot faster than applying the limits every single time. Let's find the points on the curve where our tangent line is horizontal. Now, we know that y prime is going to be 0. So let's go on and take y prime. It's going to be 4x cubed. Subtract 12x. And we want to know, when is that equal to 0? I'm going to factor 4x, leaving us with x squared minus 3. Factor, that's 4x, x plus root 3, x subtract root 3. And we've got x equals 0 is a horizontal tangent. X equals positive or negative square root of 3. We've got an equation for the position. So position is 2t cubed minus 5t squared plus 3t plus 4. Remember, velocity is the derivative of position. That would give us 6t squared minus the square minus 10t plus 3. And acceleration is the derivative of velocity, which is the second derivative of position, which would give us 12t minus 10. Finding the acceleration after 2 seconds, a of 2 is going to be 12 times 2 minus 10 is 14. That would be centimeters per second squared. The next one that we have is the exponential function, base e. You might be inclined to say that this is actually, this is big, wrong. This is not the case that we multiply by the exponent x times e to the x minus 1. That does not work because we've got a different kind of function. The power rule applies to power functions. E to the x is an exponential function, not a power function. So let's go through, and this is going to require a limit that we've seen once or twice before. If I apply this, I'm first going to factor, limit as h approaches 0, I'm going to factor e to the x. It will leave us with e to the h, subtract 1 over h. Now we can test by a table, a graph. We've seen this as h approaches 0 of e to the h minus 1 over h. That statement goes to 1. E to the x, there's no h term so there, so it doesn't do anything. It's still e to the x. We'd have e to the x multiplied by 1. We'd have e to the x. So, given our function f of x equals e to the x, the derivative f prime of x equals e to the x. Huh. Imagine that. The derivative of the exponential function, base e, is itself. That's kind of fun. It is its own derivative. Is that the only function that's its own derivative? I wonder. So what we have, derivative of e to the x is e to the x. That's another rule to remember. Let's check this out. For f of x equals e to the x minus x, let's find f prime and f prime prime. So f prime of x, derivative of e to the x is e to the x, derivative of minus x is minus 1. Derivative of the derivative, f prime prime of x, derivative of e to the x is still e to the x. Minus 1, derivative of minus 1 is 0. Another example. At what point on the curve y equals e to the x is the tangent line parallel to the line y equals 2x? Well, parallel same slope. So our slope needs to be 2. So what's that coordinate? Well, we're parallel to e to the 2x. If we've got y is e to the x, then y prime is e to the x. We want that equal to 2. And remember, if we take the natural log of both sides, exponent inside a log comes out as multiplication. It's x times ln of e, ln of 2, ln of e, that is e to what exponent equals e, that is just 1, so we have x equals ln of 2. So our point, we've got ln of 2, comma, and if we plug in ln of 2 into our function, we get 2 out. There's that coordinate. Isn't that happy? All right, try it out, take a look, come into class with any questions, and we're going to play around with this next time.